Hello, everyone. Welcome to session 8 of the Arista TAC Webinar series of 2023. Today, we are going to continue our three-part session focused on EVPN troubleshooting. First of all, a huge thanks to all of you attending this webinar. We are so glad to see all the participation, and your feedback keeps encouraging us to continue with the new topics focused on debugging, focusing on knowledge share from our TAC technical experts, and we would want to extend this to our customers, partners, and all the users of our products. We hope you enjoy this session and find it useful. Today is part 2 of our EVPN troubleshooting session, wherein we will be focusing on debugging L3 traffic through an EVPN-VxLAN fabric. This is Nilay Parekh. I am the Senior Manager of the Technical Services team, and joining me today is Upasana Dangi, who is our Senior Technical Lead in the TAC organization, and she will be walking us through today's session. As always, we actually have a solid panel of technical leads and SMEs here, and they're all ready to help with any questions that you might have during the course of this webinar. Please use the Q&A manager here, and we will ensure any questions are addressed or explained throughout the session. Also, as part of the Arista TAC webinar experience, we always use a very specific problem description and topology, which is going to focus on the troubleshooting deep dive. The plan of using a problem description is I would say it is a very unique concept that we incorporate compared to other webinars, where we actually take examples or situations from live networks, which we have seen as part of our day-to-day support observations, and then create a scenario to explain effective troubleshooting methods. This network scenario might or might not be the same network design that you have, but we feel confident that it will be a practical approach that you will be able to learn from and incorporate as part of your network operations. Topology for webinar 8 was sent out last week to everyone who had registered. Please download that and keep it alongside. That will be really helpful in actually following along this webinar. And in case you do not have it handy, please don't worry. Check the chat section here, and the topology download link has been provided. Please download that and use that for your quick reference. Also, within the chat session, we will continue to share relevant information during the course of the webinar, like useful links, feedback forms, and anything else that might be helpful. Also, for the folks who are joining us for the first time or might be joining us after a break, the TAC webinar series has been designed as a knowledge-sharing platform from our TAC experts, and it's also an opportunity for the current and potential customers to be connecting with our leads on a deep dive on technical debugging. This year, we have actually covered a huge range of topics from L2 debugging, L3 debugging, VxLAN troubleshooting, and we'll be concluding this year with the EVPN sessions. From the very first webinar that we kickstarted in 2022, we have recorded all the sessions, and these are available on the Arista Community Central page. In case you would like to revisit any sessions, or if you would like to share it with your colleagues who could not join live, all the material is available both on the Community Central page, which is for everything TAC webinar, and it's also uploaded on our YouTube channel. And on that same line, all the material from today's session, which includes the Q&A, the topology, recording, slide deck, everything will be published at the same location after the session ends. So please feel free to download that and share it with anyone you might feel would find it useful. And a final note before we dive into the troubleshooting scenario is a brief introduction about the TAC custom training. Based on the feedback we have been receiving from a lot of you during the previous webinars and just a wide interest about personalized training, we have kickstarted an offering, which is essentially training sessions led by our TAC experts. What we do in the sessions is cater to your specific network and fully customize the content based on your platforms, your features, your design, and we also do a comprehensive analysis of your recent TAC cases. This actually gives us a great view into what your network looks like, what type of problems you have been trying to address, and when we actually deliver the training, it is structured as a troubleshooting session focused specifically to your needs, and it could actually be extremely useful to anyone working on the network operations piece. And since we launched this, we have actually delivered many such sessions to our cloud titans as well as our enterprise customers, and we continue to receive great feedback on the quality as well as the content. So it is a paid offering. And if you would like to scope a session with us, or if you're just interested to actually learn more about it, please contact us at tac-custom-training@arista.com. And in case you might be interested in any general training on technologies or a certification, you can always engage the Arista training team at training@arista.com. And with that, let's go ahead and move on to the technical session. I hope everyone has got a chance to download the topology which we have shared. And please also write in your feedback when we share the form towards the end of the session. That is something that we review very closely in terms of planning the future sessions. And this is something which we'll be incorporating as we start planning topics for the 2024 series. With that, I will now hand things over to Upasana to take everyone through the world of EVPN troubleshooting. Thank you all.
Thanks, Nalay. Hello, everyone. Good morning, good afternoon, and good evening. Thank you for joining us today. My name is Upasana Dangi, and I'm from the Arista TAC team based out of California. In today's session, we are going to be covering a total of 2 problem scenarios, which we are going to use to troubleshoot packet loss in an EVPN routing environment. We will examine some common symptoms of packet loss in the EVPN fabric, and also walk through the process of isolating the problem using both the EOS CLI and the CloudVision telemetry data. So before we actually begin on our scenarios, let's just go through the different IRB models within EVPN. IRB stands for Integrated Routing and Bridging, where the VTIP that's closest to the host has the ability to locally route and bridge traffic for that host. This is different from a centralized routing model, where there's going to be only one set of gateways in the host subnet, and most ingress VTIPs are only going to be performing bridging actions on the traffic received. So we do have 2 types of IRB models that could be used, symmetric and asymmetric IRB. And in order to understand these models, let's consider a scenario where all of our VTIPs are performing gateway functions for the extended VLANs. And we can say that these VLANs are part of an IP VRF, let's say VRF Blue. In an asymmetric model, our source VTIP is going to be the one that's performing the inter-subnet routing. In this case, it's going to be from VLAN 10 to VLAN 20. And then it's going to bridge it over to the destination host VTIP. The destination VTIP is going to simply decapsulate this packet and bridge it towards the end host based on the MAC information in that packet. Now, in contrast to this, with the symmetric IRB model, our source VTIP is actually going to route the traffic into an IP VRF. In this case, it's VRF Blue. And then it's going to send it towards the destination VTIP. It's going to be the responsibility of the destination VTIP to decapsulate and then route it into the destination subnet for the end host, which in this case is VLAN 20. And once it's done that, it's going to forward it locally to the host. So how do we route into an IP VRF in a symmetric IRB model, right? This is made possible by the L3 information that is advertised in a MAC IP route. In a symmetric model, when a VTIP advertises the type 2 MAC IP route, it's going to include the layer 3 VNI and the route target of the IP VRF, along with its own router MAC. The receiving VTIP is going to take this and export it into its own IP VRF, and then use the same for routing. So in today's session, we are going to work with symmetric IRB, and we're also going to take a look at the centralized routing model. With that, let's go into our topology for today. As Nilay mentioned, you can also find the topology in the webinar chat, and I do suggest keeping a local copy open just so that you can follow along. Now, here, as you can see, we do have a few hosts, which is host 1 through host 4. They are part of either VLAN 10 or VLAN 20. They are directly connected to their VTIPs, as shown in our diagram. But just note, the location for these hosts are going to change with each scenario. Now, all the VTIPs themselves can be either bridging only or routing bridging VTIPs, for the attached subnets, and that's going to depend on the scenario. These are VTEP 1A, 1B, 2A, 2B, which are in MLAG, and we have VTEP 3, which is standalone. The VXLAN tunnel IP that we're using for each VTEP is associated with loopback 1, and all of these are going to be in the 192.168.200 subnet. All right, so all of my VTEPs, they have a connectivity to each other through a two-way ECMP, through the spine layer, which is spine 1 and spine 2. And the routing protocol they're all using for underlay and for overlay connectivity is going to be BGP. For this, each VTEP has a unique loopback, which is loopback 0. And that's being used to actually source the BGP EVPN session with the spine layer. This BGP session is going to be used for advertising the EVPN route information across all of the VTEPs. Talking about the platforms, we do have a mixture of different data center switches for our VTEP and spine layer, and all of them are running EOS version 429.4M. All of the VTEPs are also streaming to a CloudVision instance, and the instance is running version 2023.1.0. Okay, so with that, let's actually go into today's first problem statement. We have received reports of intermittent connectivity issues within the data center. But before we begin, first thing, we must assess the scope of the issue. Knowing the scope gives us a good starting point to chase down the node that could be causing the problem. So, after getting some more information, I have found a little bit more about the topology. This is a symmetric IRB topology where VLAN 10 and 20 are part of IPVRF Blue, which is extended into EVPN. All the VTEPs are functioning as the default gateway for their locally connected hosts, and all of the locally connected hosts can be either part of VLAN 10 or part of VLAN 20. Now, the issue itself looks to be flow-based, which means that some flows are successful and some are not. Flows that are successful don't have any issues, but sort of rules out stuff like congestion and general layer 1 problems. Next, we do need to do a little bit of testing to determine data points such as, is all of the traffic impacted? Is it isolated to traffic being routed or bridged, or just related to a common host or a zone? So in order to get this data point, we always recommend taking a sample set of host devices and testing between them. This gives us something tangible to work with and also allows us to observe any discernible patterns that could help in our troubleshooting process. And to save us some time, I have already run some of these tests on the applications. So if you look at the diagram, the red lines indicate that some TCP flows failed between the two host machines, and the lines in green indicate that for those connections, the test was always successful. So immediately we see a few data points. One, the issue is not isolated to any particular set of VTEPs. And two, we can see that all the hosts are able to communicate with other hosts in the same subnet, but not out of it. For example, if you look at host 4, it can communicate just fine with host 1, which is in VLAN 10, but it does have intermittent issues with host 3, which is in VLAN 20. The only exception seems to be for hosts that are connected to the same VTEP pair. So for example, host 3 is okay to communicate with host 1. So with this data, since my host machines can communicate within their subnet and to other hosts behind the same VTEP, our most likely suspect is an issue with routing in the EVPN fabric. Okay, so with this information, let's get even more specific and take one host pair where the communication fails, and then we're going to follow the path of the flow on this with CLI to understand where exactly this packet is being dropped. So I'm going to pick host 4, which is in VLAN 10 with an IP of 10.0.0.4, and host 3, which is in VLAN 20 with an IP of 20.0.0.3. All right, So for the sake of our demo, I have pre-recorded the CLI steps that we are going to undertake today, and I'm going to guide you through that step by step. So let's head on over to the CLI. Okay, so at present, I'm logged into host 4, which is connected to VTEP 3 from the topology. To begin with, let's confirm the symptom that we've been told. And for this, I'm going to try to do a telnet to host 3 from host 4. So let's go ahead and try to do a telnet to 20.0.0.3, which is host 3. And here we can see that we got a connection refused. This is expected because host 3 is not actually listening on the port and is going to send a reset. However, we can say this was successful as a test from a network perspective because we got a response back. We're going to try one more test. Let's do one more. Okay. So this one failed because we can see it's just hanging there. We're going to try just one more. Okay. So this one worked. We got a connection refused. Okay. So this does confirm what is being reported. Given that some flows work and some don't, this is usually an indicator that hashing might be playing a role, which means that non-working flows are hashing to a device that are unable to forward the packets. Now, in this type of scenarios, ICMP will not be useful if it traverses a path that is successful. This is because ICMP has no port numbers, and as such, it cannot generate the entropy we need to test multiple paths in an ECMP. That said, if the ICMP test fails, we could use it to trace the problematic node. So I'm just going to try to ping host 3. Let's see. 20.0.0.3, send about 5 packets. Okay, so the ICMP test is working, which means we are going to have to follow the packet some other way. Now, one way to follow the packet in Arista switches is advanced mirroring to CPU. Here, a copy of the data plane packet is sent to the CPU, which can then be captured through the TCP dump utility. This is a fast way to confirm if a packet is being received and forwarded with the correct headers on any of our switches. However, since this is a layer 3 network, we can actually try to reduce the number of hops we want to capture by running a UDP traceroute first. The UDP traceroute is going to send 3 probes per hop with differing port numbers that should generate enough entropy to get a snapshot of the connected paths. So on host 4, I'm going to try to run a traceroute to 20.0.0.3 and cap it to, let's say, about 4 hops. And let's say we'd say the packet is dead after 1 second. The default mode is already UDP on my machine, so I don't have to make any changes to my settings. So let's run this. I'm going to try one more test. Okay, so it does look like we have some differing results. So before we get into the details of the test, note that the IPs that we see in the traceroute are the IPs of the VTEPs that are in the path. Since all of the VXLAN traffic is going to be encapsulated, the spine layer is going to be invisible in the traceroute. Now, in an EVPN IRB deployment, typically all VTEPs are configured with Anycast IPs for the host subnets. This means that when they respond in the overlay, they could use any one of these Anycast IPs, which is not helpful to us if we are troubleshooting, because we will not be able to determine which VTEP actually originated the response. So for these scenarios, and for the traceroute to be meaningful, we want to ensure that all VTEPs respond with an IP that is unique to them in that VRF. This is also useful for distinguishing between MLAC switches that connect to the host. So in order to ensure that my VTEPs are responding with a unique IP, I have configured a unique IP in VRF Blue on my VTEPs. So let's look at this on VTEP 3. From the running config, I can see that we have 192.168.100.3 configured for loopback 2 in VRF Blue. And this is being used as the source interface for all of my ICMP traffic in the same VRF. Essentially, we can assign one unique IP to the VTEP and reuse it between different VRFs, so the result for ICMP-based tests can be deterministic in the overlay. Okay, so with that, let's go back to host 4 and look at the trace route. Based on the trace route information, given that the first hop, which is VTEP 3, represented by 192.168.100.3, it's always successful, our connectivity to the gateway seems to be fine. It's basically at hops 2 and 3 where I think things are beginning to fail and we need to investigate more. So let's go back to the first iteration of the trace route. And here we can see that in the first instance, for hop 2, 2 of the probes were successful. You can see one of the probes actually landed on VTEP 1A, that's dot 11, and the other one landed on VTEP 1B, that's dot 12, and we lost one of the probes. Similarly, in the second iteration, we lost one probe, remaining 2 landed on VTEPs 1B and 1A, respectively. And ultimately, at hop 3, we can see that some of the probes are making it to the final destination, which is host 3. So with this test, I do know that at least some probes are able to make it to the destination VTEPs, right? Destination VTEPs here are VTEP 1A and 1B. This does indicate that VTEP 3 has likely installed an ECMP route between them. But before I investigate on this VTEP 1 MLAC pair, I do want to confirm if these are the only 2 VTEPs advertising the route for host 3 that was received on VTEP 3. So for this, I'm going to move my window over to VTEP 3 and take a look at a few outputs over there. Okay, so in VTEP 3, to see the route to host 3, we're going to run a show IP route in VRF Blue. VRF Blue is our overlay for the 20003 host 3 subnet. Okay, so here we see a /32 route. And this is important because if I ran a show IP route in VRF Blue for the 20000/24 VLAN 20 subnet, it would make me think that the routing is based directly on this connected subnet. And this is actually a key difference between symmetric and asymmetric IRB. With asymmetric IRB, I would have only had this connected route, and so VTEP 3 would directly route into the VLAN 20 subnet. And it would use the data in its ARB cache to pull the MAC information of host 3, encapsulate it, and send it out to VTEP 1. However, with symmetric IRB, VTEP 3 is not going to route the packet into the host 3 IP directly, but instead it will route it to the next hops that we are learning for host 3. So how did we get this /32 route? And what are these next hop IPs and MAC addresses that we see here? The host route is populated by a type 2 route that is received by VTEP 3 from the local VTEP of host 3, which in our case is going to be VTEP 1A and 1B. If you want to see the details for the route that we are getting, we can use the show BGP EVPN route type command, specify the MAC IP for the host, which in our case is going to be host 3, 20003, and then I'm going to hit detail. Okay, so looks like we have received updates from both VTEP 1A and 1B through both the spines, and that explains the 4 paths that we see in the B route. Okay, so let's interpret this output before we go further in our debugging. This is a type 2 MAC IP route, and the details are for host 3, which is 20003, which ends in the MAC address 8A59. This MAC IP route will be originated from the local VSTEP of host 3, which is going to be VTEP 1. We can confirm that the update is coming from VTEP 1 because if you look at the next hop here, it is set to that of VTEP 1, which is 192.168.200.1. This IP is shared by the MLAC pair, And this particular update is coming to us from both spine 1 and spine 2. Further up, the route distinguisher that we see is the update that helps us determine which specific MLAC pair the update came from. For example, 192.168.111:20 is coming from VTEP 1A. Also, this update was received with an extended community for route targets for VLAN 20's MACworth, along with the L2VNI information for VLAN 20 that was mapped in VX1. This is expected because host 3 is a part of VLAN 20. Now, this is where the similarity between symmetric and asymmetric IRB stops. In a symmetric IRB model, VTEP 1 is going to send an additional L3VNI associated with the route, and it's also going to attach a route target that is associated with the VRF. Now, assuming all of the configurations match, this will allow VTEP 3 to import this type 2 MAC IP route as a host route into VRF Blue. Well, now when we import, we are going to need to determine what is the outer destination IP of the encapsulated packet and the inner destination MAC of the same packet. The inner DMAC can no longer be that of host 3 because we're not routing into VLAN 20. So how are we going to do this? The outer destination IP is still the VTEP IP, which, if you look at this update, was 192.168.200.1. And this is going to be the same received from both VTEP 1A, and if you look further down, VTEP 1B. The next hop inner DMAC, however, comes from the EVPN router MAC, which is going to be received from both VTEP 1A and VTEP 1B. All right, so since the routes are otherwise the same except the unique router MAC, EVPN is going to import it as a two-way ECMP and will send the packet to either one of these destination MAC addresses based on hashing. Okay, so with this information, let's go back and revisit that route a little bit more. From the routing table, we have confirmed that we're getting a two-way ECMP from VTEP 1, and we also don't have any other VTEPs that are trying to publish for the same host and black holing that traffic, which is good. But next, we need to figure out what happens when the connection is failing. So for this, I'm going to jump on to the destination VTEPs that are VTEP 1A and 1B MLAC pair, because VTEP 3 is a standalone VTEP, and the main entropy that is coming here is coming from the VTEP 1 MLAC pair. I am going to skip the spine layer because for the spine, this is just going to be data plane packets. And I've already confirmed that there is no latent MTU issue inside the spine layer. So let's go on to VTEP 1A and 1B. Both of the windows are open here side by side. And let's try to isolate the problem by capturing the packet that is received for host 3. The aim is to see if there is a pattern for the failing sessions. For this, I have two monitor sessions configured for CPU, and they're configured on both VTEP 1A on the left and VTEP 1B. Session spine is capturing traffic received and sent in the VXLAN underlay. And just above that, session host is capturing the traffic sent on and received on port channel 2 that connects to host 3. Now, to save us some more time, I have already run some tests of my own. And each test, I could see that the working and the non-working flows were able to hash to both these VTEPs, VTEP 1A and 1B. So it didn't look like there was something specific to any one of these VTEPs. To dig a little more, I picked a set of working and non-working flows that hash to VTEP 1B just for our comparison. So let's go ahead and move our window and take a look at them side by side. So here on the top, as you can see for the non-working flow, We see that the packet came in on the spine monitor session from host 4 to host 3, but we didn't actually send it to host 3 from the host monitor session. Conversely, on the working flow, we are actually able to see a packet coming in from host 4 to host 3 in the spine session. And we're also able to see that we are sending it out to the host on the host session. So you can see that first packet there. Also, we can see that the response coming in from host 3 is also being received, encapsulated, and sent in the spine layer towards VTEP 3. So comparing the captures a little bit more, the outer destination IP looks to be the same, which is going to be for VTEP 1, 192.168.201. And the encapsulation also seems to be correct. We can see the encapsulation here is a VNI of 2500, which is expected, and it's the VNI for VRF Blue. However, when we look at the inner MAC, that's where things are starting to look different. If we go back down to the working flow, the outer destination MAC and the inner destination MAC are both of VTEP 1B. And it makes sense because the spine is hashing the encapsulated packet to VTEP 1B. But if you go back up above, for the non-working flow, we can see that the inner DMAC is ending in 9A93, which is actually the MAC of VTEP 1A. And since VTEP 1B is not going to own this MAC, it's not going to route it. This is expected because the originated in VTEP, which is VTEP 3, has a two-way ECMP to the host routes from both VTEP 1A and 1B's MAC address. But since the outer IP for the encapsulation is shared between 1A and 1B, the spine layer can hash this packet to any of these VTEPs. Now, ideally in this case, VTEP 1B would need to receive, decapsulate, and bridge this packet to VTEP 1A so that 1A can route the packet out. However, VTEP 1B cannot do this in the host VLAN, which is VLAN 20, because the VxLAN packet was received with a layer 3 VNI of 2500, which we can see in this packet capture, and not that of VLAN 20. So to understand what's actually supposed to happen next, let's go back to the CLI, and I'm going to move our debugging back to the VTEP 1A and 1B window. Now, for such packets, ideally, VTEP 1B should have decapsulated and bridged the packet in something we call the dynamic VLAN, which is created for every VRF defined in VxLAN. We can see what dynamic VLAN is created on your switch by running the command show interface VxLAN 1. So let's run that here. Show interface VxLAN 1. Here we can see for VRF Blue, we have VNI 2500, and this is coming from user configuration. And this VNI 2500 has a dynamic VLAN of 4092. You can also see the assigned VLAN through another command, which is show VxLAN VNI. Here as well, we can confirm for VRF Blue, for VNI 2500, we have a VLAN, dynamic VLAN of 4092. Now, each dynamic VLAN is locally significant for every VTEP. However, MLAG VTEPs are going to share this dynamic VLAN. So in our thing, we can see VTEP 1A and VTEP 1B, both are using VLAN 4092. And this is needed because they also install the router MAC of their MLAG peer in their MAC address table against this dynamic VLAN. This is what enables our VTEP to receive a VxLAN encapsulated packet with an inner MAC of its MLAG peer, then decapsulate it and unicast bridge it in the dynamic VLAN across the peer link. Once the peer receives it, it can route it to the final destination. Now, in our case, this is not happening because the connection is not successful for these scenarios. And I've already pre-configured through mirroring that we are not sending a packet on the peer link. So to troubleshoot this further, let's first debug our dynamic VLAN. since we have already confirmed that the VLAN value is the same on VTEP 1A and 1B. Next, let's check if the MAC is present in the MAC address table. To do this, we can run show MAC address table for VLAN 4092. And here I can see that each VTEP has its own MAC associated with VLAN 4092, but they're not installing the MAC of their MLAG peer. One possibility is that the VLAN does not have the correct membership of the MLAG peer link, and we can confirm this through show MLAG. And so let's run that over here, and we can see here that P1000 is the peer link for our topology. Okay, so with this information, let's go ahead and run show VLAN 4092 to determine if we have a correct membership. We do see that it's present on both switches. The asterisk just indicates it's a dynamic VLAN, but I do think that we are on the right track here because I can see that it's only allowed on the CPU and on the VxLAN port. I don't see the peer link here. Now, given that the VLAN is defined, for port channel 1000 to not be a member, it is likely because this VLAN has been pruned on the peer link. To confirm this, we can take a look at the running config for P1000. And yes, it looks like we are specifically allowing only the VLANs that are user configured. And with that, we have unintentionally pruned out our dynamically generated VLAN, which is VLAN 4092. So to resolve this, I'm going to remove the more specific VLAN allow commands on the peer link, and this should allow us to forward traffic. So let's go ahead and remove that line. All right. So to confirm if this actually helped, let's go back and run show VLAN 4092. And now I can see that P1000 is part of the member list. This should hopefully mean that we can now see the MAC address populated for VLAN 4092. For that, let's do show MAC table again, 4092. And yes, now we can see the dynamic VLAN 4092 is associated with the MLAG peer MAC address on the peer link. So with this, we can actually go back to host 4 and test again. So let's do another telnet. And this worked. Let's do a couple more. We get the connection refused, it's expected. Let's do a few more. They all seem to be working now. This is because each VTEP is able to decapsulate and send any VxLAN packets with its peer router MAC address across the peer link. Now, that being said, while we have fixed our issue, one design question that does come up is whether we want to utilize a peer link at all when each VTEP is capable of locally routing the traffic. So to optimize for this use case, we do have the option of using a feature that is called EVPN-VxLAN shared router MAC. This feature would allow the MLAG VTEPs to advertise a singular router MAC in the EVPN domain. This would make each VTEP capable of routing traffic destined for this shared MAC. Okay, so let's go back to VTEP 1A and 1B and configure this. You can configure this under interface VxLAN 1. So let's go into that mode. The syntax for this feature is VxLAN virtual router encapsulation MAC address. And here we have two options. You can either inherit the MLAG shared MAC from the MLAG system ID, or you can just configure your own user MAC. Do be careful when assigning a MAC of your own, because we need to ensure that the MLAG VTEP pair has a unique shared MAC between them, and each MLAG pair has this. This is to avoid duplicate MACs in the fabric from all the VTEPs. Okay, so I'm going to go with the MLAG system ID option. And once this is assigned, we can confirm what MAC is being used by running show interface VxLAN 1. Here we can see that shared router MAC, which is ending in 971B, is the same on both VTEP 1A and 1B. This is the same MAC that is used by the MLAG feature. We can do that by show MLAG. That's the system ID, which is going to be the same as I said for the shared router MAC in EVPN. Okay, so with this, we can actually go back to remote VTEP 3, where the host route is now going to have a single next hop MAC as opposed to an ECMP. We can confirm this by rerunning the BGP EVPN route type command for that particular host 3 IP. And here we can see that we are getting updates from just the one unique shared MAC instead of multiple MAC addresses. We can also take a look at show IP route VRF blue for host 3. And here we can see that instead of the original ECMP, we have one next hop and one next hop MAC address. With this, irrespective of where the spine hashes, it could be VTEP 1A, it could be VTEP 1B, both of them should be able to directly decapsulate the route and pack it and then just route it out. This avoids the use of the pure link altogether. All right. So with this, let's go back into our slides. To sum up, we saw some intermittent issues that were affecting certain flows. On investigating further with the sample flow, we determined that the broken flow was hashing to VTEP 1B with an inner DMAC of that of VTEP 1A. Since the dynamic VLAN was not allowed on the pure link, our VTEP 1B was unable to decapsulate and bridge this packet to VTEP 1A so that VTEP 1A can complete the routing. So what we did was essentially allow this dynamic VLAN on the pure link. And once that was done, we were able to see that VTEP 1B was able to decapsulate, send the packet to VTEP 1A, which was further able to route back to host 3. Once we fixed this problem, we also tried to optimize our routing by using the EVPN shared MAC feature on both VTEP 1A and 1B. And with this feature, we no longer need to use this pure link for this kind of traffic flow. All right, so this does end our problem statement 1. And let's move on to problem statement 2. Here again, we have reports of intermittent traffic loss within our data center. And so just as we did in problem statement 1, let's first try to understand our topology and then define our scope. In this network, we're actually using a centralized routing model where VTEP 1A and 1B are the routing gateways, and VTEP 2A, 2B, VTEP 3, they're all bridging VTEPs for both VLAN 10 and 20. So I've done some surveying in my network, and I have found that applications are reporting packet loss for flows that are both in VLAN 10 and 20. Some example connections that reported loss are from host 1 to host 2, host 1, host 3, host 4 to host 3. So to get a better idea of the type of loss that was observed, I actually ran a ping test between host 4, which is 10.0.0.4, and host 3, which is 20.0.0.3. These hosts are connected to VTEP 2 and VTEP 3, respectively. All right, so from this result, I can already see there is evidence of packet drops. And when I tried to ping between other hosts, I got the same results. So now that we have a clear picture of what's going on, let's start to figure out what the problem is and fix our network issue. Now, typically, when we try to narrow down the issue when we don't have so much initial information, I would start my troubleshooting by following a sample flow packet hop by hop. However, today, I'm actually going to start from my CloudVision instance because it's already giving me some alarms for my network. All right, similar to problem statement 1, I do have a pre-recorded session for the GUI and CLI to save us some time. And I will just walk you through both of them one by one for the debug steps that we took. All right, so let's go into problem statement 2. All right, first thing is I want to see my events page over here to see if there are any alerts that are currently active in my network. I see multiple reports for my active alerts for congestion and drops on both VTEP 2 and VTEP 3, both of which are in the path of the previously mentioned sample flows. So to get more specific, I'm going to pick one of the discarded alarms on these VTEPs. Let's take the one for VTEP 3 on Ethernet 49/1. If you look at the topology, 49/1 is the uplink towards the spine switches and will carry the VxLAN encapsulated data. On expanding this event, I can see that my spine link is being heavily utilized. And if you look a little above, it's also currently dropping traffic. Coming a little bit down, if I look at my LANZ data, it is also reporting high packet buffering and drops, which is likely due to congestion. So just a quick note here, this view is only visible when you enable QMonitor streaming and LANZ features on the switch. This is a super useful way to be alerted if the device is experiencing congestion through oversubscription or bursty traffic. So back to our view. Now that I know that there is congestion, I also want to understand what type of traffic is experiencing this congestion. For this, I have also manually subscribed my terminator process to the LANZ paths on my switches, so I can stream queue information for all of the individual queues that are currently experiencing drops on my switch. For those who are interested, I have added the steps needed to get this view in the slide deck for reference later. Okay, so expanding on this view, I can see that multicast queue 10 is reporting drops. Now, on the 7050X3 platform, which is VTEP 3, we actually have 8 external queues for unicast and 8 external queues for multicast. When we say multicast here, we're talking about bump traffic, which is your broadcast, unknown unicast, and multicast traffic. MC10 here is essentially traffic queue 1 for bump traffic. Now, since I don't actually have any multicast streams in my network, there is a good chance that this is either broadcast or unknown unicast traffic that is contributing towards the congestion, both of which are unexpected in this volume in a steady state environment. So as a next step, I want to get some more statistics on the type of traffic going through these switches to pinpoint the origin of the bump flows. For this, I'm going to go to the Devices tab, and in there, I'm going to hit Traffic Flows. This view renders traffic flows that are sampled from switches through SFlow and streamed into the CloudVision instance. Just a note, any packet with a VxLAN tunnel here was received as an encapsulated frame. The VNI value indicated next to it is the destination VNI for the flow. These are flows that were mostly received from the underlay. Now, analyzing this table, I do see a bunch of known unicast traffic, and we know that because the ingress and the egress interface are defined. However, we also see a fair amount of traffic where the egress interface is listed as multicast. This is indicating that the traffic was forwarded to more than one destination interface. So to visualize this a little better, let's go into the topology view and let's take a sample flow. Let's pick host 3 to host 1. Now, from the traffic flow animation, we can see that the traffic that was received from host 3 is being flooded from VTEP 3. From the spine layer, it goes to VTEP 1B and VTEP 2B. On VTEP 2B, it's actually further flooding this across the peer link to VTEP 2A. VTEP 1B is not flooding this traffic to its peer, but directly sending to host 1. So based on the sample IPs we saw in the traffic flows, this does look like I have a large amount of unicast flooding in my network. This is unexpected because in an EVPN environment, all host MAC addresses information should be advertised by their local VTEPs through the EVPN control plane. This means that all VTEPs should be aware of all remote MACs, right? So now that we know what we're dealing with, let's jump onto the CLI for, say, VTEP 3 to better understand what destination MAC addresses are causing this congestion and our flooding behavior. Okay, so now that we're on VTEP 3, given that we already know there is high congestion on the multicast traffic queue, one option is to configure advanced mirroring to CPU to capture a sample of the traffic being forwarded on ET49/1. From that sample, we can identify the packets that are contributing to the flooding and congestion and pull their destination MAC information. Once that's identified, we can investigate why this MAC is not being learned on the switch. That said, since I do have a 7050X3 switch, another option is to simply configure LAN-Z sampling. This feature allows us to sample a copy of all packets that are currently experiencing congestion across the device. I find this feature useful, especially for any congestion-based scenario where we want to directly identify the flows that are experiencing and likely contributing towards the congestion. To save some time, I have already configured this feature on my device. So let's take a look at the configuration. Let's do a show run section mirror. The syntax is QMonitor length with a destination of CPU that allows one copy to be sent to the kernel. This copy will be protected by control plane policing and should not overrun the CPU resources. Okay. So to run the actual capture for LAN-Z mirroring, we can use the egress mirror destination port that is assigned in show monitor session. So let's run that, and we're going to use that for our TCP dump. For this particular feature, that port is always going to be LAN-Z. Okay, so let's go ahead and run our TCP dump. I'm going to use bash. So bash TCP dump -nevi LAN-Z and limit it to about 10 packets. Just a disclaimer, this is a lab environment, so I am simulating some of the background traffic on my host to mix with the genuinely affected flows. So let's ignore the higher protocol headers. That said, from this capture, we can see that all of the traffic that we are receiving from host 3, 20.0.0.3, to host 1, 10.0.0.1, is destined to a MAC address which is ending in ABCD. In fact, all of these affected congested flows are going to ABCD. This likely looks like the gateway MAC because 10.0.0.1 is outside of the subnet of 20.0.0.3. So let's check what this bridging VTEP has in its MAC table to forward the traffic to ABCD. So we can do a quick show MAC address table, and let's grep for ABCD. And this is empty. This is expected given we are flooding traffic to this MAC and also confirms our suspicion of unknown unicast flooding from our earlier CloudVision analysis. Now, ideally, the gateway MAC, which is ABCD, should have been advertised to VTEP 3 from the gateway, which is VTEP 1. VTEP 1 would have been expected to send us a type 2 MAC IP route with the reachability details for ABCD. So with that, let's see if VTEP 3 is receiving any type 2 updates from its BGP EVPN neighbor for this gateway MAC. To see a list of neighbors, you can run show BGP EVPN summary. So let's run that here. And for us, it's going to print the 2 spines that we are peering with. You can pick any one of them. Let's take 102. To see the routes received from this neighbor, we can just run show BGP neighbors, add the IP and the address family. We want the received routes, and we are looking for the type 2 MAC IP routes, so MAC IP, and for the gateway MAC, which is 001C, ABCD, ABCD. Okay, so this is empty, which indicates that VTEP1 has not advertised this MAC. So at this point, since we are not really receiving anything from VTEP1, we have absolved VTEP3 as the problem node and shifted our troubleshooting focus to the VTEP1 MLAC pair. So let's move our window to VTEP1A and 1B switches. And let's troubleshoot over here. So going to VTEP1A and 1B, the MAC address ABCD is likely the shared virtual MAC that was configured on these gateways. And if you want to confirm this configuration, we can actually run show run section virtual. This is going to show us the running config. And yeah, we can see that this MAC address is configured on both the VTEP1 and VTEP-B switches. This MAC is going to resolve to the shared Anycast gateway IP for both VLAN 10 and VLAN 20. And this is going to be shared by both the MLAC peers. Okay, now that we know that VTEP1 owns this MAC, let's see if VTEP1A and 1B are actually trying to originate this EVPN update for the virtual MAC. Again, so to see the type 2 route that we originate, you can do show BGP EVPN route type, again, MAC IP for this particular MAC. I'm going to hit detail. This is also empty, and that explains why all of my bridging VTEPs are going to be flooding inter-subnet traffic everywhere. So the next question is, how does a gateway originate a type 2 MAC IP route for the virtual MAC in an EVPN environment? On Arista switches, the Anycast virtual MAC is tied to something called as the virtual VTEP IP or the VVTEP IP. This IP is shared by all the routing VTEPs in the EVPN domain. So when a type 2 route is originated for this virtual MAC, the gateways are going to use the virtual VTEP IP as the next hop for this update. And this is necessary because if there are multiple routing VTEPs and they all use their unique primary VTEP IPs, it's going to cause all the downstream bridging VTEPs to keep flapping this gateway MAC between all of the primary IPs. You might have seen in deployments where all EVPN VTEPs have IRB enabled. We actually don't need a virtual VTEP IP configured. And that's just because all gateways are going to locally own the same virtual MAC. However, in our topology, the one that we're using today, because we have centralized routing, we do need to advertise this virtual MAC to the bridging VTEPs 2 and 3, and this has to be sourced from the VVTEP IP. So let's see if we have something configured. We can do show interface VX1, and here I can see that we do have a primary VTEP IP, which is 192.168.200.1. This is shared by the MLAC pair. However, we do not see a reference to a VVTEP IP over here, which explains why the MAC IP route was not generated. So let's go ahead and try to configure one under the VXLAN source interface, which for us, as I mentioned earlier, is loopback 1. You can configure just about any IP, just ensure that it is advertised in the BGP underlay. I'm going to go ahead and configure an IP address of 192.168.200.100/32, and this is going to be the secondary IP on this loopback. Once this is confirmed, let's rerun show interface VX1. And now we can see that the virtual VTEP IP is populated and it's present on both the MLAC peers. Okay, so now let's see if VTEP1 is able to originate the MAC IP route. Let's do this through show BGP EVPN route type MAC IP, and let's hit enter. Okay, so we can see that VTEP1 is originating the MAC IP route It's doing that in both VNI 10 and also VNI 20. It is correctly using the VVTEP IP, which is 200/100, instead of using the primary IP, which is being used for the VXLAN tunnel. Okay, so with all of this addressed, the MAC advertisement should now be received on VTEP 3. So let's go back a step to our window for VTEP 3 and confirm if the BGP route is being received. For this, we're going to rerun that earlier command for BGP received routes. Same MAC address, let's hit enter. And yeah, looks like we're receiving this from both MLAC peers through the two-way ECMP that's coming in from the spine. Next, we should also see if this MAC has now made it into the MAC address table. So let's go back and run show MAC address table. Again, pipe grep for ABCD. And as you can see, this is being learned on both VLAN 10 and 20 over the VXLAN interface. So let's go even further. Let's go check under the VXLAN address table. For that, let's hit show VXLAN address table. And again, we're going to grep for the gateway MAC. And here we can see that the gateway MAC on VX1, which is ABCD, is now being learned over the VVTEP IP, which is 200/100, and it's being learned on both VLANs 10 and 20. Okay, last step, let's also confirm if the congestion on this device has subsided, because now all the traffic should be known unicast. We can check this by doing show interface counters rates. I'm going to pipe it to non-zero values only. And yeah, for 49/1, now the egress rate has dropped to about 50%, which is similar to what I have on the inbound. This, if you remember, was previously around 98 to 100% when we saw it in CloudVision. This is because now in the steady state, we only have to send one copy of the traffic destined to the gateway MAC, which is towards VTEP 1. We no longer have to try and replicate a copy of this on all of our ports, including over our VXLAN flood list. Okay, so if you're on the right track, at this point, we should now be able to ping between host 4 and host 3 without any loss. So let's go back to our host 4 window and see how this is going to work. Okay, so on host 4, we were previously seeing loss. So let's rerun our test. Ping to host 3. And nice. It looks like we seem to be succeeding with our test, and we don't see any packet loss. So this does confirm that we have found and fixed our issue. So with this, we can end the CLI and return back to our slides. Okay, to sum up, we saw intermittent loss in traffic, which was attributed to high congestion on the multicast queues that cater to bum traffic on our 7050X3 switches. The bum traffic was mainly identified to be unknown unicast flooding in VLANs 10 and 20 for the gateway MAC, which was ABCD. This flooding was on only the bridging switches, which is 2A, 2B, and VTEP 3, and that was causing drops on the uplinks towards the underlay, and it would have mostly affected routing traffic. Further investigation confirmed that the gateway MAC was actually not being advertised in EVPN because both VTEP 1A and 1P did not have a virtual VTEP IP configured, which is needed in a centralized gateway scenario. Once we added this virtual VTEP IP, this enabled both our VTEPs to advertise this MAC to VTEP 2 and VTEP 3, allowing them to follow normal unicast forwarding rules. This removed the congestion that we were seeing on all of these bridging VTEPs, as we were no longer making multiple copies for traffic that was intended for the gateway. Also, on the side, I have listed the commands that we used for today's session, which can be used for reference later. I have also linked some useful TOIs and Community Central articles. There are good reading materials for all of the topics that we have discussed today. And with that, I hope that today's session was useful, and I'm going to hand it back to Nilay to help conclude the webinar.
Awesome. Thank you very much, Upasana. That was a great session with some really useful information covered today. Folks, as Upasana mentioned, we do have a lot of good commands and articles that you can leverage for troubleshooting. And it's always a nice idea to approach debugging both through the EOS CLI and Cloud Vision, as both of these will have its own benefits. Also, in addition to the webinar content, I will also encourage everyone to explore the Arista Community Central in general for various articles. This is going to include technical overviews, troubleshooting guides, all of these things which are written by Arista TAC. And as we start wrapping up, a couple of quick reminders. First is about the feedback form link that has been shared in the chat here. We would be really keen to hear from all of you about this session and any other suggestions that you might have. And second is that all the material from today, the recording, slide deck, Q&A is going to be posted on the Arista Community Central at the same location. Our next session, which will also focus on EVPN and will wrap up our 2023 series, is currently scheduled for October 25th. And taking a cue from the kind of deep dive troubleshooting that you just heard from a TAC expert, if you are interested in scoping a custom training session for your network operations team, please do get in touch with us at tac-custom-training@arista.com. We will start wrapping up Q&A in the background, and we will hopefully see you all again on October 25th for the final part of EVPN series. Thank you so very much for your attendance. Hope you found it useful and have a great day ahead. Thank you so much all.